Welcome back again. Thank you for joining me for our second discussion on section 2. So we're going to further our conversation about these lines of best fit, these linear regression models. And what we're going to focus on today is the idea that we know that no line is going to be a perfect fit, right? In the real world, we're never going to have data that perfectly fits a line. So we want to have a way to discuss what's happening, like those errors, all right? And those errors we're going to call residuals, okay? So a residual, all it is the difference between the observed value of a response variable and the predicted value based on the regression line. Okay, so there's two ways to think about it. I always think residual, observed value minus, or observed y minus predicted y. Using symbols is going to be that. And this, unfortunately, is one of those things that is not going to be on the formula sheet. So this is something you're going to have to memorize and just be accustomed to doing. Now, again, visually, what we're talking about is if we're tracking these, what's happening is here, this would be the residual for this point, okay, from the line to the point. This one, this would be the residual. So the residual are those vertical distances, okay? The distance between a predicted y value and the line, okay? But we're taking the observed minus the predicted, okay? So let's talk about, again, what this means in the grand scheme of things. So grand scheme of things, here's some more data. So below is some data on the relationship between the price of certain manufacturers' flat panel LCD televisions and the area of the screen. We like to use these data to predict the prices of televisions based on size. Okay, so we have a table there with some information, and we have a scatter plot. And here they also are really nice, and they gave us the prediction line, okay, or the line of best fit, sorry. So the first thing, part A, is if I just give you the line, I could actually ask you to draw it on that scatter plot. Now, the issue is we're used to graphing lines saying, oh, I'll start at the y-intercept, and then I'll use the slope to go up from there. That's not as easy to do in this case, obviously, because if you look at my y-intercept actually isn't even showing on the axis, all right? So, and this has been able to happen occasionally where they ask you to draw that line in. So here's my piece of advice if they ask you to draw a line. To draw the line, you realistically only need 2 points, right? So I'm going to use an area of 100, okay, because notice that's actually showing here. So all I'm going to do, I'm going to plug in 100 into the formula. So I'm going to take 105.74 plus 0.77 times 100. So I'm just plugging in that area, or that, and getting 182.74. All right. And I'm going to plug in another one. I'm going to plug in maybe, let's say, 200. Plug in 200 into that formula. That's going to give me 259.74. Okay, so again, to do this, I'm just going to make 2 points, okay, find 2 points by plugging them in, and now that's how I'm going to get a general idea of where that line is going to be. Here, fortunately, again, I kind of chose poorly because 182 is going to be a little bit off, so that's going to be down here somewhere. So again, unfortunately, that didn't work perfectly. But 200 and 259, that's going to be about here. So if I make that line, again, it's not perfect, but again, at least you have a general idea of where that line is. Okay? Now, find the predicted price for a TV with an area of 437 square inches. All right, so 437 square inches. Again, if we're going to make that prediction, well, I kind of already showed you how to do that, right? To make that prediction, all you're going to do is plug in 437. So 105.74 plus 0.77 times 437. So here our predicted value is going to be 442.23. Now, find the residual for the TV with that screen size. All right, now, residual, again, residual, we're talking about the observed value, so the actual value y minus the predicted. Okay, that's always how you calculate residual. All right, so here we have the predicted right now. The actual has to come from the true data point, okay? That's where the actual y comes from. Well, here the fortunate thing is that actually gives it to us, right? That original table told us that actually it was 375. So all I have to do is that calculation to get negative 67.23. All right. And it says show the distance on the graph that would represent that residual. Okay, so on the graph, what that would look like is it would be this distance right here. Okay, and so interpreting this in context, so what does this mean for us? Okay, well, what it means is notice the predicted value was a lot bigger than the actual value, right? Because this is predicted, that's actual. So notice the predicted was a lot bigger than the actual. So it's a little bit backwards, but that negative residual actually means we over predicted, didn't it? So here, the interpretation of this is our regression line over predicted the price of a 437 square inch TV by $67.23, okay? Because that residual only is for that specific screen size, right? So you do have to be very specific that here our regression line over predicted that price of that particular TV by $67.23. So again, that is what a residual means. It talks about how off was your observed Y from your predicted Y. So interpret the slope of that regression line. So again, I'm going to keep bringing all of these things back because you guys are good at it that day, but we have quite a bit of chapter 3 to go still. So I want to make sure we're still good at it by the time we get to that test. So remember slope. Slope says when x goes up by 1, it tells you how much y is predicted to change by. X is area. So basically, whenever we have an extra square inch, so when we go up by 1 square inch, the predicted price is going to change by, and here I believe the slope is 0.77. So when the area of the TV increases by 1 square inch, the price goes up by, or is expected to go up by 77 cents. Here, describing the association. All right, so describing association, again, that is another way of asking FODs. All right, so here we did see a very linear pattern here. It was very strong. So here, remember, there is a strong positive linear association between TV screen area and the price of that TV. So again, whether they talk about analyzing the correlation coefficient, talking about the association, the nature of the relationship, all those things, always FODs. Suppose a company puts a 20 cent per dollar, or puts 20 cents per dollar of the price of the TVs back into advertising for their product. Give a point estimate, a single value for the change in the average advertising money for each additional square inch of TV. All right, so basically the change in average advertising money per additional square inch. Well, we can relate price to the area. So price per area, isn't that the slope? Right? So we have a relationship between the price and the area, okay, of the TV screen. And now this is saying 20 cents per dollar of that is going into advertising. Okay, so every inch of TV, they get 77 cents. And now of that, they're putting 20 cents into advertising. So if we need a single value to make a prediction relating TV area now to this advertising, well, that would just be the 77 cents, and then 20 cents of that is going into the advertising. So 0.77 times 0.2. So we're talking a little over 15 cents. So for every inch of TV screen, about 15 cents is going into advertising for those TVs. This is going to be a really good one, okay, because it's a little tricky. So again, that's going to be a really good one as you come back to study for your upcoming test. I do recommend having that one starred. It is going to be very important for you. I specifically put this in here to give you a little hint for something that's coming up. So again, be very deliberate going back, and please do reference that question for me. Let's move into another example. So in a college algebra class, the Minitab or the following is a Minitab output for data collected on quiz averages and scores on the final exam. All right, so they want to know what is the residual of a student who had a quiz average of 85 and got an 82 on their final. So let's recall residual. Actual y minus predicted y. Okay. Now here, if we look at what's going on here, so here's a piece of the table that we want to look at. Remember, we always want to look at the coefficients of the variable, or sometimes they call them predictors. So you can see the average, the quiz average, okay? The quiz average is creating our slope, right? And then the constant, or the y-intercept, is going to be the 12.12. Now, we could make the equation from that, but the cool thing is they already did, right? So here they already put the slope with the quiz average, the y-intercept off on its own. So basically what I'm seeing, the quiz average are the x values, and then the final is what we're predicting. So we're using the quizzes to predict how they're going to do on the final. So when I'm looking at this, I'm seeing that 85 as an X, okay? That is a quiz average. And this student actually got 82 on their final. So that is an actual Y value, okay? Not a prediction. So that 82 goes right there. Now, right now you may think that there's no purpose in that 85. It doesn't go into the residual calculation. However, it kind of does, because if we need to find the predicted Y, well, the predicted Y, don't we need to actually use that X? So the X actually goes into the linear equation, that regression line, to help us find the predicted Y. Okay, so again, this is where it's really interesting, because you need to know really carefully where to put each of those numbers. So when I plug that in, I get a predicted Y of 75.935. So that's my predicted Y. So the residual would be 6.065. And if I had asked you, I didn't, but if I asked you, what does that residual mean? Well, what it means is our line actually underpredicted that student's score. We predicted they'd get about 76. They actually got an 82. So we underpredicted the performance of this student. Okay, but again, I would get into the habit whenever they ask you about residuals, I would start labeling out everything they give you. I would start by putting this down, okay, what the residual equals, and then start labeling here. So I labeled, I know this is an X, that's actual Y. All right, so that means I need to find predicted Y using that X. Okay, so it's kind of a puzzle that you need to be able to fit together for me. So let's look at this one now. A student who had a quiz average of 80 has a residual of 3.5. What was the student's actual score on the final exam? All right, so here we're talking about residual. So as soon as I see residual, immediately this comes to mind. Okay, immediately I know I'm going to be using that. Now this time I'm actually given the residual. And then a quiz average, that's going to be an X value again, right? We're using those quizzes to talk about their actual final score. And so we want to know, what was that student's actual score? But notice we're missing both pieces still. So that's interesting, I guess. So what I want to discuss is that X value. Again, if I plug that X value in, that X value actually gets me the prediction, right? So that's why whenever they give you an X is very important, because you can use that X to find the predicted value. So all I have to do is plug that in, 12.1 plus 0.751 times 80. So this student would be predicted to get 72.18, and we're looking for their actual score. Now here the cool thing is, this is just a little bit of algebra, to be honest. If I want Y, don't I just add the 72.18 over? So their actual score was 75.68, or about a 76 on the final. Okay, so it is important not just knowing what residuals are, but also how to manipulate where you can plug things into the equation. I can give you pieces of information and ask you to find the other thing. I can give you the residual and ask for the actual, okay? So again, just know how to manipulate that formula for me. Um, so these residuals, actually in the conversation, you've already heard me use this term before. I've used the term least squares regression line. And this is why it's called that, okay? So the linear regression, I already taught you yesterday, both of those are actually types of this least squares regression line. The calculator does it automatically for you. But where it's coming from is this idea that that you want to minimize those residuals, right? If we want our line to be as accurate as possible, we obviously want as little error as possible. So we want to minimize those residuals. The problem though is the residuals for that line, you have the same amount of negative and positive, right? Your line is going through the middle in a way that it's going to cancel out all the positives and negatives. So when you add up all, if you add up all the residuals, you're going to get 0 overall. Okay, so that's why we have to square the residuals. We square them so now the negatives and positives don't balance out anymore. Okay, now everything's positive, and that gives us the value that we can minimize. Okay, so that's why here you're trying to minimize the square of the residuals. That's the goal, is to making this line, and that's the program that your calculator has been embedded with to be able to do. Okay, you're able to, or it does all that minimizing for you. So again, there's 3 ways you can do this. We talked about getting the calculator to do it for you, having a Minitab output, and then there is one more way that you can do this. Okay, and that is sometimes you can know the means and the standard deviations of um, of this data. Okay, and if you're given both the means and standard deviations of both x and y, you can actually still find these equations. And the way you do that is using these formulas right here. Okay, now let me show you though on your formula sheet. So can you take out that blue formula sheet, please, for a moment? So if you take out that blue formula sheet, I'd like you to flip to the back, to the descriptive statistics. I flashed this at you in the first video that I made, okay? So this is the least squares regression line. Okay, and just like I said, notice it used different things here. So this BO, the BO is your y-intercept, B1 is your slope. Okay, so again, the book uses different variables than your formula sheet does. I would recommend probably using the formula sheet way of doing it, because that's how you're going to recognize it on the actual AP exam, and the resource you're going to have, the resource you'll have for my test as well. So here, if you notice, if BO is your y-intercept, then it shows you right here that that is how you calculate that y-intercept. Okay, so that's the calculation for the y-intercept. And then notice a little bit below it, here's B1. We said B1 is your slope. Now, something to notice, B1 is used in the formula for the y-intercept. So what that's telling me is whenever I'm given the situation, if they just throw, here's the mean standard deviations at me, obviously I'm going to have to calculate the slope first, then I'm going to calculate the y-intercept, okay? Because obviously I need the slope in that calculation of the y-intercept. So again, I would actually go and I would mark all of this on my sheet, on the formula sheet that I gave you, so you can use that as you're studying. Because this is going to be something you will need for the test, and rather than memorize it, why not just have it sitting here for you? So let's talk about how this is going to work, okay? So some people think that the behavior of the stock market in January predicts its behavior for the rest of the year. Take the explanatory variable X to be the percentage change in the stock market index in January, and the response variable Y to be the change in the index for the entire year. We expect a positive correlation between X and Y because the change during January contributes to the full year's change. Calculation from the data over an 18-year period gives that information. Find the equation of the least squares line for predicting full year change from January change. And again, I already give you the hint, find slope first, then the y-intercept. So again, you're going to be using these formulas that I just had you highlight in your packet. Okay. So again, in your packet, it references this. So this is what I'm going to base all my stuff off of. And so what that tells me, again, it tells me calculate slope first. Well, according to this, slope is going to be B1. It says the slope is the correlation R, then SY over SX. All right. So again, this is really just a computation now. So R is 0.596. SY is going to be 15.35. SX is going to be 5.36. So really, it's just plugging in those values, okay? Plugging in those numbers that you're seeing. So all I have to do is plug that into the calculator. 0.596, then times that 15.35 over the 5.36. That's going to give me about 1.707 for my slope. Okay, so that's my calculated slope. Now, obviously, I'm going to need the y-intercept. According to this, y-intercept is the BO. And according to your formula sheet, BO is the mean of y minus the slope that you just found times the mean of x. And again, this is what I mean of why it's so important that you calculate slope first, because you obviously need slope in this calculation. So the mean of y is 9.07 minus the slope, which is 1.707, times the mean of x, 1.75. Now this is where you can do a really slick trick. I've shown some of you this already as you've been working, but if you have been doing all this in a graphing calculator, remember, instead of typing this number in, if you just use that answer command, it'll pull down the exact value that was already in your calculator from the first one. So here, 9.07 minus that 1.707, or the answer that was most recently in your calculator, times 1.75, and you should get approximately 6.083. So again, really all this is piecing it together in the formula, or in those formulas, and now you can finally tell me that your equation, that y hat, is going to be 6.083 plus 1.707x. All right, so again, really cool to be able to go through that. And all it is following patterns, following that formula. Okay, that's literally all you have to do for me. Now, the last part. The mean change in January is 1.5 or 1.75%. Use your regression line to predict the change in the index in a year in which the index rises 1.75 in January. What does that imply about the point with the two means? So here, it's saying this is what I should be plugging in. So when January goes up by that mean, what's it doing? Well, let's plug that in. 6.083 plus 1.707 times that. Well, when January changes by that mean, let's see how the whole year changes. So 6.083 plus 1.707 times the 1.75. That's how much the year is predicted to change by. Now, that number should be kind of familiar to you. So basically, what this is trying to show you is when y actually changes by the mean, it goes, or the year changes by its mean. So basically, what is that saying? Well, that's saying that this point, the point with the two averages, is actually on the regression line. The way that this formula is built, those means, the mean of x comma the mean of y, that point always actually exists on the line. Okay? And again, that's just a cool tidbit. Sometimes shows up in multiple choice. So good thing to maybe know. But again, just an interesting consequence of how this formula is made is those means always actually land perfectly on that least squares regression line. So I think that's enough. That is a lot to take in already. So we're going to call it good for the notes there. Then, of course, use the remaining time to start working through the homework and the readings and stuff like you always would.